Hello everyone, my name is Nur Azza Afiza binti Jailani from Chemical Engineering Department and I am the secretary of this project. To start off, I'm going to enlighten you about the background of this project. It is a well-known fact that MDF board is highly preferred due to its affordability and versatility. However, it also has its own drawbacks. For example, MDF board has poor strength and it is non-water resistant. Therefore, the Autumn board is created to be an alternative for MDF board. It is made from dry leaves and epoxy resins, which is aimed to have a much better quality than the conventional MDF board. There are two problems that have been identified. First and foremost, MDF board has poor strength since it is not designed to accommodate heavy loads. Plus, it is also non-water resistant, which implies that it would cause wood swelling after being exposed to water for a long time.
Hello, my name is Muhammad Isri Shahmi Benizban, ID number 180000996, and I'm from Petroleum Engineering as our combiner. Why dry leaves as our material? It's because leaf cuticles have unique roles that assist the plant operate and develop properly. Cutin creates an insoluble hydrophobic barrier, which means it does not dissolve in water and instead stays put to protect the leaves. This trait of leaf can be applied for this board to use its water-resistant trait to make the board waterproof. Epoxy is referred to a large set of reactive compounds with an oxygen or epoxy ring present. Epoxy resins can be mixed with a variety of curing agents and modifiers to get the desired characteristics for a particular application. The properties of epoxy resins are high strength, low shrinkage, excellent adhesion to various substrates, effective electrical insulation, chemical and solvent resistance, and finally low cost and low toxicity. Now, I will be explaining about Autumn board prototype fabrication procedure. This is the video of procedure of making Autumn board prototype. Material and apparatus: hardener, resin, dry leaves, mold, scale, and mixer. Step 1. Shatter the leaves in small pieces. Step 2. Weight the materials with the ratio of 6, 2, and 1. Step 3. Mix together all the materials and put it in the mold. Step 4. Leave it below the sun for 3 hours.
Hello, I'm Lin Xionghua, ID 180024881. I'm from Mechanical Engineering. We separate into two parts. First is soaking test and second one is tensile test. So soaking test is done to determine how well does a material absorb water and how will it affect that. So the apparatus and material needed for this is first containers and second will be the MDF and outer box specimen where the thickness is 7 millimeters. So to do this test, first both of container is placed in a room at room temperature. Then the container is filled with water. Then each specimen is immersed in water and after 2 days, the observation of changes of the board is recorded. So next will be tensile test. So tensile test is done to determine the mechanical property of a material. So from a test, we can obtain a stress strain graph where the stress is obtained by dividing force over the cross-sectional area of the board and the strain is obtained by dividing change in length over the initial length. So now I'll explain a little bit on the mechanical properties that can be obtained from the graph. So first is U point. U point is a point that indicates the limit of the elastic behavior and the beginning of the plastic behavior. Ultimate tensile strength is the maximum strength that the material can withstand when being pulled or stretched before breaking. Fracture point is a point where the final point is recorded before it fractures, and Young modulus measure the tensile stiffness of the material, or in other words, it shows how easily can material be bent. So the apparatus and material needed is first buckets, flexible water pipe, G clamps, clamping mechanism, welding caliper, and then outer board specimen where the thickness is 7 mm. So due to some test limitation, the standard tensile test specimen size according SME is not available, therefore a new specimen is needed. So to do this, we just need to do a simple static stress simulation, then we'll get the shape and dimension of the specimen. So to do a tensile test, first the apparatus is set up shown in the figure. Then the red bucket is filled with water and the initial length of the specimen is recorded. Then, water is siphoned from the red bucket to the blue bucket until the specimen break or the bucket is fully filled. The red bucket is always filled with water to make sure the siphon process continues. The mass of load and changes in the length of the specimen is recorded every 10 seconds, and the test is repeated for the Autumn board. Now I'll show you the result of the tensile test.
Hi, my name is Izafami bin Ahmad Fuad, and my ID number is 1800262 and I'm from Petroleum Engineering Department.
Now I will talk about the results. So for the first test is tensile test. Tensile strength of the MDF is 2.4 megapascal while the atom board is undefined, but we know it's greater than 4.5 megapascal. As we can see on the picture of the graph stress versus strain on the left side, it shows that atom board is stronger compared to the MDF board, and the Young modulus value for the MDF is 17.951 megapascal and the atom board is 18.977 megapascal. As we can see, the end of the experiment, atom board, which is on the top, is maintained on the shape while the MDF board is break down. Now we go for the discussion part. Atom board stronger than MDF board. Why? This is because of the urea-formaldehyde inside the MDF board and epoxy resin inside the atom board. This is the battle of these two materials. As we know that epoxy resin is harder and stronger compared to urea-formaldehyde, that's why atom board better than MDF board in the strength test. In the soaking test, we can see that MDF board is totally wet and easy to break even in one hand because of both material, especially the wood residue absorbing the water. So that's why the formation easily to deform, while atom board is dry and strong because of epoxy resin and the dry leaf itself prevent the water from go inside. Even in dry leaf, it have originally wax layer on top of every dry leaf, so it's prevent the water from go inside and maintain the shape of the board. Next is limitation and recommendation. The first limitation is time because we need a longer time to prepare for the test and the process of fabrications, and load because we need a more load to calculate the strength test of the atom board, and the machine, we need a proper machine to make the board so easier for us compared to the manpower. And the recommendation for this project is we need to use a proper machines and for testing and fabrication so that we can get the more accurate results and the higher performance of the board, and also we can cut the cost. So that's because we know the ratio, perfect ratio between the dry leaf and the epoxy resin.
Hi, my name is Faiz Shafiq. Now let's go over the economic consideration for our project. Factoring in the capital cost of 55 ringgit, we estimated that we need to sell 25 quantities of it to reach a break-even point. How do we get that number? Factoring in the capital cost would result as of RM2 ringgit 20 cents to produce a single atom board. Once we reach a break-even point, the cost to produce atom board will be lowered to 1 ringgit 90 cents or 13% lower. Or we could also reach a faster break-even point by increasing profit margin. As of now, the cost to produce atom board is 43% higher compared to MDF board. But we highly believe that the cost can be significantly be lower by scaling our production, such as buying raw material in bulks.
In conclusion, all objectives were successfully achieved. From our findings, it is clearly observed that atom board showed better resistance to water. In addition, atom board exhibits higher tensile strength compared to the conventional MDF board. However, due to the absence of proper lab equipment, errors might have occurred. Thus, in the future, it is highly recommended to utilize proper lab equipment to improve the accuracy of the results obtained.